Okay, before we get started today, one announcement. Graceland Portable Buildings, which is over in Cunningham, if you know where Cunningham is looking for an IT person. I was stunned at this visit. They came and visited earlier this week, and I thought, Cunningham? Portable buildings? It's a pretty big operation. We've got like 12 sites around. They've got pretty decent IT installation. So anyway, they're looking for somebody. I beg your pardon? Yeah, it's over past Mayfield. Yeah. Yeah. Oh, okay. Cunningham. I have contact information. They're looking for employees and interns. So, and I have an announcement up on Canvas. It'll tell you a little bit about what's going on. I also have an announcement. It's kind of way ahead because this thing I think is in April, but for the Patterns of Distinction, which is a thing the Center for TSM puts on. Speakers usually good. Honestly, I haven't looked at the speakers this time, so I can't comment on it yet. But it's usually a good piece. I would try to plan your schedule around being there. Depending on where we are, we'll see what this class conflicts with and see if we can work it out. So, okay, what we're going to start into today, we did kind of an overview of what we're going to be talking about and kind of set the parameters on it. We're going to start looking at some of the fundamentals on this now. As I mentioned, when it's all said and done, it doesn't matter what technology we're using. What we're doing in here is moving human voice across a network. That's fundamentally an analog process. I mean, we're analog beasts. That's just the way we're wired together. So what we're going to do is realize that when we start talking about voice, what we're really talking about is something that is wired into us to work a particular way, and we're changing the way that works. Of course, we've developed ears and interface between ears and brain, but this whole thing is driven by acoustic energy. When I speak in here, what I'm doing is varying the pressure in the room. Your ears are designed to respond to that. And so they convert that into a meaningful, I hope it's meaningful, message. So this is the process that we're inserting electronics into. Okay, you got to keep that in mind. You know, we're the end user. An awful lot of the stuff we do in this major, the end user is another computer or a display device or something like that. The end user in what we do is a human. And that puts different parameters on some of the stuff we do. Okay. Kind of a review. When I show a waveform in here, it's just generally easier to talk about a sine wave. Yes?
So basically, vibrations create air pressure.
Uh-huh. Yeah. When I speak, my vocal cords alternately push air up and they pull back. And so they if you want the $5 words, it's compression when they make the air pressure higher, and rarefaction when they make the air pressure lower. The number of times they do that in a second is the frequency of what we're talking about. I'm getting ready to cover that here. So what we're looking at, when we talk about signals in here, it's easier for me generally to show you a sine wave. Obviously, we don't speak in sine waves. But the math works the same way, the systems work the same way. It's a whole lot easier. If you think my drawing's bad with a sine wave, wait till you see me try to do a real voice waveform. Anyway, what we talk about in this is the amplitude of that pressure wave is cyclical. So for a half cycle, I'll increase the pressure. It'll go to some maximum value and then come back down. We'll cross where we started. We'll actually go down, decreasing the pressure on that cycle, get to some lower value, and then come back up to the 0 point. Amplitude in acoustic energy is loudness. So if I'm going to increase the amplitude, I'm going to yell. Okay. Similarly, frequency, and you've dealt with this in other forms, frequency, when you talk about acoustic energy, is the number of cycles we complete in a second. Now, be careful applying math you learned for electrical principles or radio principles to this. The medium's different. We're using air. You ever played the game of when you see a flash of lightning, you count, and you can tell how far away the storm is? How do you know how far away the storm is? 1001, 1002, 1003. If you get to 5, it's a mile away. If you get to 10, it's 2 miles away. Why the difference? Because acoustic energy moves about 1,000 feet a second. Light moves 186,000 miles per second. So, but they work similarly when we start talking about frequency. What we're saying is over a period of time, a second in almost everything we deal with, we're going to complete some number of these high pressure, low pressure cycles. And that frequency is what we as humans detect as pitch. So if you hear a bell, you know, you think, oh, well, that's a middle C if you're a musical person. I'm sort of musical, but I have no idea where middle C is. If I hear a lower tone, it's lower in frequency. If I hear a higher tone, it's higher in frequency. I'm going to try to record a demo for this. I didn't get it. I had one, and it has been corrupted. So, but frequency is pitch. The last thing we look at is something that's a little harder to get a handle on. We developed with ears that could hear a very broad range. We can hear from about 25 hertz to about 22,000 hertz. Now, actually, those of us in this room can't do that because your hearing at the very high end starts diminishing almost as soon as you're born. If you're a rocker or you like your stereo very loud, then you've probably knocked the top off of this more effectively than than everybody walking around. That's your ears. Your voice, the part we use to communicate, how we make formants for language, doesn't have near that range. It actually extends from about 200 hertz to 3,500 hertz for the important stuff. Now, you know, some of these guys that can sing way down in the basement can hit 100 hertz or even a little bit lower. And some of these ultra sopranos can hit, you know, 5,000 or 6,000 hertz, maybe. That's not where most of the information for communication and voice is. When we're having a conversation, we're using a much narrower slice of this. Okay, and that'll be important when we start looking at coding, because it gets into coding. Gets into the amount of bandwidth, and the highest frequency determines how many samples you have to take. Now, bandwidth is kind of the overall quality of a voice. So let me play you a couple of clips. This clip is bandwidth limited to that voice band only. Well, it will be as soon as I can play it. And, of course, the amplifier's turned off. Shoot. Hang on a second. Thought of everything else, but I didn't check that before we started. Oh, well, they've torn it apart. Bear with me. I didn't realize this had been taken apart. I didn't do my homework. Okay, so, hold on. Let's see if I can get it on. If I can get it on this, I'll bring some speakers over and play it.
At the tone, the time will be 4:56 and 20 seconds.
You hear how it kind of sounds like she's all pitched up? That's what happens when you limit bandwidth. Let me play another clip. Let me play that one again, and then I'm going to play another clip for comparison.
At the tone, the time will be 4:56 and 20 seconds.
Let me play another clip right after it.
AT&T. Thank you for calling the GE Card Services
Hear the difference?
Credit Card Servicing Center.
By the way, in trivia, the first woman was named Jane Barbie. She was the voice of Belle South for decades. And the second one is a woman named Pam Conley, who's still around, alive, well, doing voices for all sorts of things. So,
I read somewhere that people actually tried to mimic her.
yeah.
Because they were so used to her.
Jane Barbie, the first one, just worked for Bell South and happened to have a nice voice. And they said, well, come on, will you record these for us when they're playing? She just sort of worked into a job. Pam Conley was the one they found after doing all this research about what was the most optimum voice to go through noise and be understandable and all that stuff. So anyway, the difference between those two clips, that narrow one that sounded kind of pinched, is limited to our voice bandwidth only. Now, you could understand what she was saying just fine. You got all the words. But it's just not as pleasing a sound. It's not as full. It doesn't have the richness. That's what the bandwidth gives you, is a better tone. Now, we'll come back and visit that when we're talking about coding, because you end up playing a game. When you start using voice over IP, you can select which coding method you want to use. When you're using PSTN, guess what? It's selected for you. And so I can choose to move higher quality audio. The trade-off is it uses more bandwidth for me to do so. So we'll look at that kind of relationship. For now, just realize that our ears can hear a lot wider signal than our voice can generate. And since we're moving the human voice, we're going to look at networks that limit audio to that passband.
Are tone and fidelity the same thing as you said? Tone
Not quite. I use them interchangeably in here. If you start talking to, golden-eared audio people, they'll tell you there's a difference. I've never had it explained to me to where I could repeat it, so I use the terms interchangeably. Okay. All of this came about so that we could do what we're doing right here, communicate at close range. This works, and this is what we're wired up for, to be 10, 12, 15 feet apart. The problem is that's only where it works natively. And you can think about having this. You ever chase somebody down the street trying to get them to, hey, well, what's the problem? They're far away. Okay? When you launch energy into any medium, you start getting attenuation immediately, which is a fancy term for saying the signal loses power as it traverses the medium. The medium in this case is air. And so as I move further and further and further away from you, less of that signal power gets to your ears. Now, I can compensate by making my voice louder. That's why you yell when you're trying to get somebody's attention further away. We can only do that to a certain point. After a bit, we're going to get to the point where we simply can't overcome that acoustically. You only have so much lung power. If you're out on the lake, you can probably barely make yourself heard maybe a mile away on an absolutely calm day. If you're out in the desert, a little more than that maybe. Now, can we increase the acoustic energy over what we do here? Sure. You can put a PA system in. I live down across from the middle school. I can understand every word during a football game. No problem. But that's not really feasible. For one thing, it takes a huge amount of power. And for another thing, they're using tens of thousands of watts of power. I live a mile away, and I can hear it, but if I went another mile away, I wouldn't be able to understand it. So it's not, for one thing, an efficient way, and for another thing, there's only one channel. We'd all have to take turns talking, and we don't do that well. So what we're going to do is convert this to another form of energy and use a network that can move at a longer distance. Of course, we're talking about electricity and what we do. When you convert one form of energy to another one, the process is called transduction. You've probably heard the term transducer. A transducer is a device that converts one form of energy to another. We have one right here. That's a transducer. It takes electrical energy and turns it into photonic energy. This is another one. This is taking electrical energy. No, it's taking acoustic energy and turning it into electrical energy, which is how I'm doing the recording. And that's what we do in our telephone system. The microphone in the handset transduces acoustic energy, pressure waves, and it converts that into a varying electrical signal. Now, the particular trick we do is that we make this varying signal match the frequency and the amplitude changes from the acoustic energy. And then I reverse the process on the other end. So think about what we've done. I'm speaking words. I have varying pitch. I have varying amplitude. I'm varying the shape of those so that you have words. The microphone is taking that, changing the energy to a different type of energy, but it's keeping those frequency, pitch, and loudness, amplitude information intact. At the other end, I use a different transducer called a loudspeaker, run that varying electrical current through it, and what it does is transduce that back to varying acoustic energy. The advantage, I can run this signal a really long way. Okay? I can do things with it that I can't do with acoustic energy. Okay? So that's what we're going to be doing with it here. Typically, and this is several slides, I'll let you go through it, but typically these systems will vary the voltage on that wire. Honestly, in this class, we're not real concerned about exactly how that works, with a couple of notable exceptions that I'll cover when we get there. Mostly, we're just kind of taking this that, yeah, you stuff acoustic energy into a microphone and somehow it makes an electrical signal. What we are concerned about is the signaling on the wire, and we'll get to that later in the semester. Oh, whoops. I'm going to jump over and look at another presentation for a second just to kind of show you where we're going. We're not going to go through this whole one.
Are there certain atmospheric conditions where sound travels farther than others?
Sure are. You'll see this slide again next week when we go over this material. Whoops. This is what Alexander Graham Bell put together. He didn't actually invent the phone. He was pretty successful at getting the patent office first. There were several people working on the same idea. But basically what he did was come up, or one of his assistants came up with a transducer that took acoustic energy and made it into electrical energy. Remember, this is 1870. Electricity was pretty new in terms of something that was more than a curiosity. And he fed that directly across to a speaker. Great. How many of you have been on a one-way phone call? I have. It's not always the most fun phone call I have, but there are few exceptions. They're not very useful to do that way. What we're going to do is take this whole idea of transduction, acoustic energy, and where that information is bounded, and we're going to apply it to how we create a system to move voice across a network. Now, to get there, this is we're at the point that the exercise I'm going to leave up for you this weekend is covered. So let me give you a little map of where we're going. We're going to take a look at some fundamental things you have to do in any telephone system. Doesn't matter if it's tin cans and string, voice over IP, PSTN, whatever. There are a few basic things that every system has to do. They do them differently, but they have to accomplish those things. And I need you to have a handle on that before we go any further. We're going to learn some of the nomenclature that we need to do so that we can discuss this instead of waving arms and, doing it as big as a bread box and things like that. We're going to learn some nomenclature so we can discuss as well. That'll probably take us through next week, since we lose Monday, and into the week following. We will use next Friday. We will not be in lab next Friday. We're just going to be back in here. I will probably use more than an hour of it. Okay? Probably won't use 2 hours. So I had actually planned on doing 2 full lessons in here today, but with the long weekend and just starting, we'll pick it up Wednesday and we'll run from there, because I'd really rather not have the stuff we're going to start covering suffer from the long weekend syndrome. So I do have an exercise up that covers some questions over what we went over today. I realize it was a short class. Thanks for hanging with it. That exercise will be due Wednesday morning at 8, and I'll see you Wednesday. Be safe this weekend. So.